Today I'm going to discuss about operational amplifiers. The operational amplifier, Opamp, is a direct coupled amplifier with a very high voltage gain, very high input impedance, and very low output impedance. Originally, Opamp was designed to perform mathematical operations such as summation, subtraction, multiplication, differentiation, integration, etc. in analog computers. That is why it is called operational amplifier. In diagram of widely used Opamp IC741, we can clearly see that the positive plus V and negative minus V supply voltages are connected to pins 7 and 4 respectively. No connection is required to pin 8. Pin 6 is the output terminal. Pins 2 and 3 are called the inverting and non-inverting inputs respectively. If a signal is applied to the pin 2, the output is inverted, that is 180-degree out of phase with respect to the input, while no phase shift occurs when the signal is applied to the pin 3. Terminals 1 and 5 are used to make. Let us discuss the concept of virtual ground. The figure shows the basic circuit of an inverting op-amp which employs negative feedback through the resistor R2. The negative feedback voltage through R2 tends to cancel the input signal at the point A and tries to keep the point A at ground potential. If Vi be the potential at A, then output Vo equal to Av into Vi. Since the open loop gain Av tends to infinity, for a finite Vo, we must have Vi tends to 0. Further, since input impedance Ri tends to infinity, practically no current enters into the op-amp input terminals. Thus, there is a virtual ground at the point A. The word virtual is used to imply that though the point A is effectively connected to the ground, no current actually flows into this short. Obviously, it is not the actual ground. However, the concept of virtual ground makes the analysis and understanding of many op-amp circuits very simple. Opamp has a wide variety of applications. Here we considered only a few of the important applications. First, we discuss about the inverting amplifier. The figure shows the basic inverting amplifier using an opamp. Since the input resistance of the opamp is ideally infinite, practically no current enters into the opamp. Therefore, current I through R1 is also the current through R2. So using the given equations, we finally find the closed loop gain of the inverting op-amp is Vo by Vs is equal to minus R2 by R1. The negative sign indicates that the output is 180-degree out of phase with the input. Comes the non-inverting amplifier. The figure shows the basic non-inverting amplifier using op-amp. Here the signal is applied to the non-inverting terminal. Now if V2 is the potential at the point A, then the differential input is Vs minus V2. So the output voltage Vo is equal to Av into Vs minus V2. Since Av tends to infinity, for a finite Vo, we must have Vs minus Vs. V2 minus Vs tends to 0, that is V2 equal to Vs. Thus, there is a virtual short at the input terminals of the op-amp. Since the input impedance of op-amp tends to infinity, practically no current enters into the op-amp. So almost same current passes through R2 and R1. So from the given equations, using Kirchhoff's current law, we get Vo by Vs is equal to 1 plus R2 by R1. The output Vo is in phase with the input Vs. In the previous slide, we see that if R2 equal to R1, the voltage gain equal to minus R2 by R1, which is equal to minus 1, so that the circuit provides a unity voltage gain with 180-degree phase inversion. The amplifier then acts as a voltage follower, that is a non-inverting amplifier with unity gain. Adder or summing amplifier. The figure shows an op-amp adder or summing amplifier which provides a means of algebraically adding a number of voltages, each multiplied by a constant gain factor. Since the point A may be treated as virtual ground, we can write the summation of I1 plus I2 up to In as I. Now solving the equations, we get Vo equal to minus Rf by R1 into V1 plus Rf by R2 into V2 up to Rf by Rn into Vn. Now if we equate all the resistances, then we get Vo is equal to minus Rf by R1 into V1 plus V2 up to Vn. Thus the output is proportional to the algebraic sum of the inputs. Next, let us discuss about the integrator circuit. The figure shows the circuit of an integrator whose output is proportional to the integral of the input signal. As the open loop gain and the input impedance of the op-amp are infinite, the point A may be treated as a virtual ground. Almost same current flows through R and C. Therefore, using the Kirchhoff's current law, we get I equal to Vs minus 0 by R is equal to dq by dt, that is equal to minus ddt of cv naught, where we take q equal to c into 0 minus vo as the instantaneous charge on the capacitor. Hence the output voltage comes out to be vo equal to minus 1 by rc integration of vs dt. Thus the circuit provides an output which is proportional to the time integral of the input signal. But not the least, let us talk about the differentiator circuit. The figure shows the circuit of an Opamp differentiator whose output is proportional to the time derivative of the input. Since the point A may be treated as the virtual ground and practically same current flows through C and R, we can write I equal to dq by dt, that is equal to ddt of CVS, which is equal to 0 minus VO by R, where we take Q equal to CVS as the instantaneous charge on the capacitor. Therefore, VO comes out to be minus RC into dVs by dt. It shows that the output voltage VO is proportional to the time derivative of the input voltage Vs. This was a short discussion about operational amplifiers, which has a wide range of applications in as voltage amplifiers, oscillators, filter circuits, and many types of instrumentation circuits. Hope you enjoyed watching this video, so thank you.